Semiconductor physics. Band theory of solids. Every atom is associated with its own energy level. When two atoms are placed apart, then they do not interact. Two atoms close together causes particular energy level to split into two energy levels. Band theory of solid explains how the energy bands are formed within solid. Energy level splitting in a solid. Diagram A. Energy band structure of the solid corresponding to the actual spacing of the atoms in the body. 2. Energy level splitting as a function of distances. 3. C. Discrete energy levels in an isolated atom. So energy bands in semiconductors, the energy level splitting energy band configuration in silicon crystal as shown here. Distance 2n levels 4n electrons. Valency band. The band formed by series of energy levels containing the valence electrons is called the valency band. It may be completely filled or partially filled with electrons. Conduction band. The band formed by the energy levels of free electrons that have broken their covalent bands is called the conduction band. Conduction band is the next permitted energy band. It may be empty or partially filled with electrons. Forbidden energy gap. The energy gap between the valency band and the conduction band is called the forbidden energy gap or forbidden band or the band gap. This band is formed by a series of non-permitted energy levels above the top of the valency band and below the bottom of the conduction band. Energy gap is denoted by the Eg and it is the amount of energy supplied to excite the electron from valence band to conduction band. It is measured in electron volts. Classification of solid on the basis of the energy band diagram. Insulators. Materials which do not conduct current is called insulators. Conduction band and valence band separate with a large energy gap which is greater than 5 electron volt. Semiconductors. Materials which have the conductivity lies between the insulators and semiconductors are called the semiconductors. Energy gap is small and it is order of 1 electron volts as shown in figure. For conductors as shown in figure, materials which conduct current is called the conductors. As the valency band is overlaps with the conduction band, energy gap is 0. If an electric field is applied to the solid and electrons in the valency band has easy access to move in conduction band and current flows through the material. Type of semiconductors. Intrinsic semiconductors and extrinsic semiconductors and the doping. Intrinsic semiconductors. N. Extrinsic semiconductors, one of the N-type semiconductors. P-type semiconductors. Concept of the holes. Fermi level and Fermi energy. For conductors, the highest occupied energy level at 0 Kelvin, absolute temperature is called the Fermi level and energy corresponding to its energy is called as the Fermi energy. For semiconductor, Fermi level is the reference energy level and it corresponded to the center of gravity of conduction electron and valency hole. Fermi level is the reference energy level and it corresponds to the center of the gravity of conduction electron and valency hole. Fermi Dirac function. F of E is equal to 1 by 1 plus exponential of E minus EF by KT. F of E is the function that gives the probability that particular energy level having energy E capital is occupied by an electron at temperature T Kelvin and where EF is the Fermi energy, K is the Boltzmann constant. For conductor, the highest occupied energy level at absolute temperature is called Fermi level and the energy corresponding to it is called the Fermi energy. This is a reference level for the semiconductor. So effect of temperature and on Fermi function. This is for the conductors. Fermi level in intrinsic semiconductors. At 0 Kelvin, number of electrons in conduction band equals to the number of holes in valence band. That is, Ne is equal to Nh which is equal to Ni. Fermi level lies in the middle of the band gap. Temperature is not zero, depending upon the effective mass of the electron and hole. Effective mass of the electron and hole. That is Eg by 2 plus 3 by 4 kT into log of me star by mh star. Fermi level in p-type semiconductors. The number of holes in the valency band are greater than the number of electrons in the conduction band. So the Fermi level shifts towards the valency band, and which temperature Fermi level shifts towards the F1. N-type semiconductors. The number of electrons in the conduction band are greater than the number of holes in the valence band. Therefore, Fermi level shifts towards the conduction band, and with temperature, Fermi level shifts towards EFI. Variation of Fermi level with impurity and the concentration. Variation of impurity and concentration in N-type semiconductors. Figure A. At low impurity concentration, figure B. At moderate impurity concentration, figure C. At high impurity concentration. Drift current. What is the drift current? The current due to motion of the charge carriers or drifting of the charge carriers under the application of the electron field is called the drift current. Drift current density is given by JE drift is equal to NE by mu E and PE mu E HE. Mu E mu H are the constants called the mobility of the electron holes, and J drifted is equal to JE electrons drift plus holes drift. Diffusion current. The directional movement of the charge carriers due to concentration of gradient is called the diffusion current. Diffusion current density is due to electron is given by ED and dN by dx, and holes is given by EDH dP by dx, where DE, DH are the diffusion coefficients for the electron and hole respectively. So J diffusion is equals to electrons diffusion plus holes diffusion. Conductivity of semiconductor. Conductivity of intrinsic semiconductor sigma I is equal to NIE into mu E plus mu H. Conductivity of extrinsic semiconductors. For N-type semiconductors, sigma N is equal to Ne mu E, which is equal to Nd E mu E. For P-type, sigma P is equals to Pe mu H is equal to Na E mu H by P-type, where Nd, Na are the concentration of the donor and acceptor impurities. Junction diode. So PN junction diode is just like a current value. It allows a unidirectional flow of current. Diode conduct only when it is in forward bias, not in the conducted ideally reverse bias. It is used as a rectifier. Diode has non-linear voltage current characteristics. Formation of a PN junction diode. Holes are the majority charge carriers and electrons are the minority charge carriers in P region. Electrons are the majority charge carriers and holes are the minority carriers in N region. PN junction is bounded between the P-type and N-type semiconductor. Physical structure of the symbol. Biasing of a junction diode. Biasing of a diode. Forward bias, reverse bias. Energy band diagram of PN junction diode at equilibrium. In forward bias mode as shown in figure. In reverse bias mode as shown in figure. VI characteristics of the junction diode. Pictorial history of the transistors. Bipolar junction transistors or transistors means transfer the resistor. The transistor can be thought of a device which current travels from low resistance to high resistance path. We have PNP transistors and NPN transistors. The pictorial of the structural diagram is as shown in figure. Modes of operations. Common base mode and common emitter mode and common collector mode are the energy band diagram of transistors as shown in figure lie here. NPN as shown in figure here. Hall effect. When a current carrying conductor is placed in a transverse magnetic field, potential difference is generated in the direction perpendicular to the both current and the magnetic field. The voltage developed is known as the Hall voltage and the effect is known as the Hall effect. Applications. Determination of the type of the semiconductor, concentration of the charge carriers, mobility charge carriers, magnetic field and Hall coefficient.